Okay, today we're happy to have Max Ruhdorfer from Stanford to tell us about forward muons and a muon collider.
Right, yeah, thank you. Thanks for the introduction. So I'm going to talk about the physics potential of forward muons and muon collider. I'll get back to that in a second. First, I want to acknowledge my collaborators. So this is work in collaboration with Ennio Salvioni and Andrea Volta, and it's based on these two papers here. The first one came out about a year ago. And the second one, I might have changed the 10 to 11 soon, but the paper is essentially done. It's just micro changes that have to be done now. So it might be out even this or next week. All right. So as you probably noticed, there has been a renewed interest in muon colliders. And I say renewed interest because it's actually not the first wave of interest in a muon collider. And to see that, the best thing to do is just go on Inspire and look for papers that have muon collider in the title. And then what you'll find is there were only 3 ways where the muon collider got more attention. And now you would probably ask, why should we pay more attention now? And the difference is that now there's also a bigger interest in the theoretical community. Before, most papers were by accelerator physicists and experimentalists, but now even the theoreticians get excited about it. And you might be able to see an exponential rise here. The year is not over yet, so it might still go up. And also, there's also a considerable R&D effort to really find out if a muon collider is possible, how it is possible, and with which parameters. And there are even already 2 organic collaborations that have been formed, the International Muon Collider Collaboration, which is the European effort that started at CERN, and now there's also a US Muon Collider Collaboration, which started, sorry,
Forgot about the back door.
which was started very recently. And the International Muon Collider Corporation is conducting the EU design study, which has, I think, to report at 2026, so in 2 years. And also, as we all know, there has been a strong support from P5 for a muon collider, or at least an R&D in a muon collider. So I want to argue that now is the time to study the physics potential of a muon collider. And now is still a time where we can actually give inputs to experimentalists, what we would want from a muon collider, what we would need in order to do the physics that we want to do. So the question is, what detector specifications are actually needed to get the full potential out of a muon collider? And this work goes into that direction. Okay. So why is a muon collider interesting, or what are we even talking about? So first, just to get us all on the same page, so what they propose in the IMCC collaboration is a stage design with 2 stages. The first one would be a muon collider at a center of mass energy of 3 TeV with an integrated luminosity of 1 inverse autobahn, after which it would be upgraded to stage 2 with a center of mass energy of 10 TeV with an integrated luminosity of 10 inverse autobahn. And I probably don't have to convince anyone that a muon collider would be a great machine if it's possible to build one. Because it would really be the best of both worlds. It would be an experiment at very high center of mass energies, similar to hadron machines, while you're still at a clean environment of a lepton collider. So just as a simple example, so this curve shows here where the production cross-section, pair production cross-section at a proton collider, what the equivalent production cross-section would be at a muon collider. So if we go at a 100 TeV proton collider, then this would roughly correspond to a 10 TeV or a little bit above 10 TeV muon collider. And that will also be our benchmark for the rest of this talk. I'll mainly talk about a 10 TeV muon collider. Now, something that I think is not appreciated enough is that a high energy muon collider could also be called a Higgs factory. And it actually produces more Higgses than what we traditionally call Higgs factories. So if you look at FCCE, RLC, or CLIC, those produce around 10 to the 6 Higgses in its lifetime. But a muon collider, well, depending on the center of mass energy or the luminosity, you could go up to 10 to the 8 Higgses in its whole lifetime. It would make it comparable to high Lumi LHC, but you're still at a much cleaner environment. So you could really use all of these Higgses. Of course, FCCHH would have many more Higgses, but also a much more challenging environment. Now, all of these Higgses, or most of them, would be produced through vector boson fusion. And altogether, at 10 TeV, with an integrated luminosity of 10 inverse autobahn, we would produce 10 million Higgses through such vector boson fusion topologies. And with so many Higgses, you can really test rare Higgs decays, for example, invisible Higgs decays, and you can also constrain Higgs couplings at the per milli level. So a Muon collider is really also a Higgs factory, even though people don't call it that. Now you might say there has to be a catch somewhere. And I wouldn't call it a catch, but there's a challenge. Muons, as we all know, decay along the beamline and they radiate photons, they radiate in principle any electroweak radiation. So your beam is contaminated by all of these decay products and secondary products. And you don't want any of these products to be scattered into your detector because it would harm the detector and would also be a huge background. But there are ways to mitigate that. And the current mitigation strategy that is foreseen for a Muon collider is to put tungsten absorbers, tungsten cones, in the forward region that are supposed to absorb these electrons and photons. And simulations show that this could reduce the beam-induced background, which is what we call these secondary particles, by 3 orders of magnitude. And after that, it's really you can really handle it with timing measurements to really get rid of it almost completely. So here in this picture, it's pretty nice to see. So everything in dark gray or black here would be the detector volume, while the greenish cones are these absorbers. And the problem with this approach is that you limit the detector coverage. In principle, block out the whole forward region here. And in the current design, these absorbers block out the whole region, which is less than 10 degrees from the beam axis.
So what is it exactly that, so beam-induced background, what is it that this is getting rid of? If you didn't have these, you would have what?
Electrons, photons.
But they're in the same, I mean, naively, I would say, oh, but they're in the same region where the tungsten nozzles are. So why do you just don't, if you just don't look there? What is, somehow that gets out even further from this region that you're cutting out with these tungsten nozzles?
So, well, as far as I understand it, you have all of this beam-induced background, which would hit your detector apparatus somewhere and then would be scattered into the detectors. So you want to really absorb them before they can be rescattered into your detectors and
so somehow the tungsten actually, there's less scattering from the tungsten.
Exactly.
And there would be, if the
yes.
tungsten weren't there, then
Yes,
you would
yes.
just have interactions all along there.
Exactly, yeah.
Okay.
Exactly.
So it's kind of a very, very messy version of Pilot. It's like what they have at the LHC, but it's much worse, I guess.
Exactly, yeah. That's essentially what it is, yeah.
And Pilot are additional hard scatters of protons in the bunches.
Yeah.
And we also have beam-induced backgrounds, where a proton hits something and makes pions and muons, and so
Right.
you're just kind of traveling along with the bunches.
So it's not even proton. Proton could be a proton pion or something. Yeah.
Yeah.
Okay. Okay, thanks.
All right. So, like I said, with the whole foil region, if you like it in eta it's larger than 2.5, is cut out. So you can't measure anything there. So you lose the whole forward region. But the benefit of colliding muons is that high-energy muons are penetrating particles. So our idea was that you could actually place a detector somewhere further along the beamline, somewhere behind the whole detector apparatus here, and just detect the muons that penetrate through the tungsten nozzles. And I want to argue that just having information about these muons, everything else would be stopped, just the muons would go through, but only the information about the muons would allow you to do interesting physics. So now you would ask probably, why should we care about these four muons? So as already mentioned before, a high-energy muon collider is actually a vector boson collider. So what you're scattering is typically not the muons themselves, but radiated Z's or gammas or W's, which take part into the hard collision and produce some fine state X. And if if you collide neutral currents, then they all come with potentially detectable muons in the final state. And these muons are typically very forward, so they would be caught up, if there's no forward detector, you would not see them at all. So they would go completely unnoticed. So it is really important if you want to study vector boson fusion and vector boson scattering processes, which are almost any process that are in high energy muon collider. And even more important if you have signatures with invisible particles. Because just imagine your final state here is invisible, then you would not even see it at all in the detector. Yes.
So even for the production of heavy resonances, you're saying that's the case, or just in the lower energy regime?
It depends on what you're interested in, what kind of resonances. For example, if
X weighs a TeV, as massive a TeV, then are those muons really not being deflected much?
they get deflected more if you have a very heavy resonance. It's mainly
If you have two massless particles, these are almost massless, right? Creating a particle at rest, then they can definitely just keep going forward, right? So kinematically, a perfectly forward muon is completely compatible with a very heavy object at rest, right?
I see. You're saying it's just the PT of X.
Yeah, and of course it's not perfectly like that, but then this thing is still peaked. I think even at high energies, there's a lot of the full muons go forward.
yeah, you still have a lot of forward muons. That is correct. It gets a little bit better with higher masses. That is also correct. And it also always depends on how exactly you produce them. Most of my examples will be through a Higgs portal, for example, and then if you have an on-shell or off-shell Higgs, then typically you have very forward muons. I'll get into that in a second.
And sorry, this may be a total detail, but
Sure.
those tungsten nozzles, any idea of how many radiation lengths they are? Do you have any technical information on?
I know where to find it, but I don't I don't know it by heart. I'm sorry.
Thanks.
Okay. Now the question is, how forward would these actually be? So this is exactly the question also that we were asking. In order to estimate that, let's just look at something that's produced through Z fusion. So if Z's are emitted by the incoming muons, then their PT spectrum is peaked around the Z mass. Which means we can just do a simple estimate if the center of mass, if the invariant mass of the X final state is much smaller than the beam energy, then it's just pure trigonometry to find at which angle the muons would exit the detector. So this would just be the momentum in the Z direction over the beam energy. And depending on the beam energy, this would have different values. So for a 10 TeV collider, so beam energy of 5 TeV, you would be talking about an eta of around 4.7, which is pretty forward, so it's 18 millirad. And this is just the peak of the distribution. For 3 TeV, it's a bit less, but it's still problematic, still outside of the coverage of the main detector. And if you look at it in an example of Higgs, BVF Higgs production, then the red curve is for 10 TeV, and the eta of the muons is, as we just estimated, peaked around 4.7. But careful, this is a logarithmic scale. So if you cut it at 2.5, where the main detector ends, you would lose almost the complete signal. You would see almost nothing. So in order to really use these forward muons, you have to go up to an eta of around 5 or 6. Then you would get most of the signal at a 10 TeV collider. Also, just a small side comment. This was for Z emission, but you also have photon emission. Photons, the PT spectrum does not have a peak at the Z mass, but it goes all the way down to the muon mass. So it would get much more forward, but the spectrum distribution is logarithmic, so even if you cut at 6, an eta of 6, you will still also cover a lot of the photon spectrum. All right. So our task, what we tried to do, was to identify physics scenarios which can be tested with this forward detector, or which can only be tested with this forward detector, which you would not be able to test without it. And then, as a second step, we also wanted to identify detector specification that we would need to even say anything about that. Because measuring or even detecting these forward muons is not simple. So we classified it in more or less 3 different steps of how much information you have about these forward muons. So the simplest thing would be just to tag them, just to know that there were forward muons, and only that would give you some information. Then, if you in addition have some angular measurement, this would also allow you to do more refined analysis for vector boson scattering and vector boson fusion, which I'll also come to later on. But what we really want is, of course, angles and energy. And I just wrote down a couple of things that you could actually do with those, and I classified them in terms of direct search for new physics or precision measurements. So in terms of precision measurements, if you just tag the muons, this will already help you with Higgs couplings. You can lift flat directions. For example, you can distinguish between ZZ fusion production and WW fusion production, because WW fusion would not have any muons in the final state, just neutrinos. But even if you then have angles, then you can use, in fact, that Andrea called interference resurrection. So you can disentangle the interference between different helicity configurations of vector bosons, which you would lose if you have an inclusive measurement. Because if you integrate over all of the angles, then typically the interference drops out. But I'll talk more about this later. An example of that would be CP Whiting Higgs vector couplings, which you can constrain just with having angles. And if you in addition also have energy, then you can also do new physics searches. One example is Higgs portal models, which I'll talk about later. So this is one perfect example which you can only do with forward detectors, because otherwise the final state would be completely invisible. At least if the Higgs portal scalars are long-lived. Also, electroweak dark matter would benefit a lot from a forward detector, but I'll not talk about this today. And then something that's in between a direct search and precision measurement is invisible Higgs decays, which was part of our first paper, which I'll talk about. And you can also do a measurement of the inclusive Higgs production measurement in ZZ fusion. So the only thing that we didn't find was something that only requires tagging or angles, and would be a direct search for new physics. So if you have any ideas, let us know. This would be a pretty interesting addition to what we have so far. Okay, so the plan of the rest of my talk will be, first this is not our work, this was done by Patrick Mead and collaborators. I'll just give you one slide summary of what it would do for Higgs coupling measurements. Then I'll talk about if we have everything, energies and angles, what it could do. I'll explain most on the example of invisible Higgs decays, which shows all of the main ingredients that you need. And then I'll just quickly comment on inclusive Higgs production cross-section measurements and Higgs portal scalars. And at the end, I'll talk just about angular information about the forward muons, and say a bit more about interference resurrection and how to measure CP by Higgs vector couplings. Okay, before I get really started now, any more questions?
So if you wanted to compare, if I wanted to think about comparing the way I should think about a muon collider with something like LAP, right? Mm-hmm. The beam constraint obviously to some extent does depend on being able to see things in the forward direction, right? So the more you degrade your ability, I mean, it's that's what a hadron collider is, right? You sort of have, and so is there a sense in which, because I'm thinking about your blank thing there, is there a sense in which there are searches where you might be you really want the beam constrained, and this helps you out? Is that a legitimate way to maybe think about one aspect of the impact of this?
I'm not really sure.
Like some invisible things or something like that? Why don't you go on?
Yeah. Let's
Okay,
talk
we
about
can talk about it later.
Yeah.
Anyway.
The blank was also for only doing the tagging.
Yeah, tagging or angles. No energy resolution.
So that's not a beam constraint. Sorry, obviously the beam.
Yeah, 'cause I was wondering.
The
too.
beam constraint, you need to know the energies.
Yeah.
But if you have the angles, maybe that, I don't know.
Okay, anyway,
Yeah,
that
Maybe,
makes,
maybe you can do something.
yeah,
Yeah.
okay.
All right. So first, if you just tag the forward muons, already as I mentioned before, so this was work by Patrick Mead and his students. If you just tag the muons, then one thing that you can do is you can distinguish between ZZ fusion production, for example, in terms of Higgs couplings, and WW fusion production, because only in ZZ fusion you have muons in the final state. So if you take a muon, then, or if you detect two muons, then you know it was ZZ fusion. So if you, so this helps you, first of all, to suppress some backgrounds. For example, there are different backgrounds that they consider which have only one muon or two muons or no muons at all. So you can distinguish between those. But it also lifts flat directions between coupling measurements. So for example, if you don't have any information about the final state muons, then WW and ZZ fusion are degenerate. You don't have any idea if your Higgs was produced through Z's or through W's. So what they found here, this is just in the Kappa framework for a 3TV and 10TV muon collider. They found percent level and sometimes sub-percent level precisions that you could determine these kappas. But once you add for muon tagging, up to they took an eta of 6, and you see that mostly kappa W and kappa Z benefit a lot from that. But it's not only those two, also because of the improved fit, you also get an improvement in most kappas. So this is all that I want to say about this, because this was not our work. But even if you can just tag them, only then you can do something. All right. So the first thing that I want to focus on is invisible Higgs decays.
Sorry, can I just
Yes.
also, so who kind of, or what group, or who sort of first started thinking about these forward muons?
That's an interesting question, because it turns out, so there's an old Delphis card for the muon collider. I don't know how old it is, must be 5-6 years old by now. And already there, they had the option of a forward muon detector. But there was no paper or anything that went into that direction after that. Also, many people forgot about it, and at
What's
some
the first
point,
paper that you know of?
the first paper that I know of, well, Patrick Mead, they mentioned their paper, but that was already at the same time when we were also working on it. So we discovered it because we were driving constraints on for a muon collider, and assumed a perfect coverage up to an eta of 6 for muons. And then we found out about all of these absorbers and everything,
I see.
and tried to make a case to actually also measure muons up to that area.
Okay, thanks.
Yes.
This is maybe a stupid question. So the coupling tables, are all of these up for grabs after HLLHC is over? In other words, do you do better with the muon collider for all of the, I can never keep any of these straight. So are these already better than what you can get at HLLHC?
Yeah. They're definitely better than what you can get from a linear HC. Yeah, you typically can't get to percent level of most of them.
Got it.
Okay. All right, invisible Higgs decays. So, as already mentioned earlier on, at 10 TeV you produce around 10 million Higgses, and just alone by statistics, it has a huge potential. Just a few, so the only ones that, if the Higgs decays invisibly, the only one that we can actually see are the ones through ZZ fusion. And only those would be 620,000. So you would have a lot of Higgses produced through ZZ fusion at the muon collider. And let's just compare this to the Higgs invisible branching ratio in the standard model, which is 0 of 10 to the minus 3. This means even within the standard model, you will produce 1,000 invisible decays, which we would be able to observe for a detected coverage up to an eta of around 6. So up to here, more or less. This means this will even allow you to look for invisible Higgs decays, which are smaller than the standard model value. So here you really have to split up into a contribution, which is the standard model value and some additional BSM contribution. So if we So this means we would, because we have thousands of those, we would get around a percent level or maybe 10% level precision on just the standard model contribution. So we could theoretically probe BSM contribution to the invisible Higgs decay of 10 to the minus 4, which would be much, much smaller than what the LHC can do right now. So the current bounds are like 10%. So this would be almost...
So this also you think is tagging is enough? You just have to know.
No. So
No,
for this you
talking.
also need energies. So in all of the section you need energies and angles.
Okay.
Okay. So this was just a naive back of the envelope estimate. Now let's go a bit more into the analysis. So what kind of backgrounds we have for something like that? So you produce the Higgs in ZZ fusion, you have 2 muons in final state and missing energy. So one of the irreducible backgrounds is of course the production of 2 neutrinos, which has missing energy, and there you can not really do much to get rid of that. Then you have the standard model background, so the standard model decay into invisibles, which you also have to include if you assume that you'll be this sensitive to it. And then the most important background turns out to be missed particles. So in principle, anything with 2 muons plus X, anything else, and which, since the only place where we can detect particles which are not muons is in the main detector, so anything that's outside the main detector will be lost and will look like missing energy. Anything outside the central detector will be missing energy, or also if it's too soft to be detected in the central detector, then this will also be lost and will contribute to this background. The largest contributions here are QD radiation, so you have an additional photon that's attached to U plus mu minus, or you have 2 fermions, or diboson production, for which we took W plus W minus as the biggest contribution. What we also did was, which is also important, we included QD radiation for the signal and some of the backgrounds. And actually doing that is not as simple because none of the currently available Monte Carlo tools do a matching between QD shower contribution and a fixed order calculation. Because what you would actually want to do is, so here I show the PT of the muon pair, and the important curves here are the brown curve here, which is just Weber scattering, so you have mu plus mu minus in the final state, plus QD showers, so some soft and collinear photons that you can observe. But this has a huge rate, which however drops quickly, but at some point you have the fixed order calculation of one additional photon, which takes over. And what you would want to do is to match those, because there's not really a clear separation when you should use one or the other, but right now this is not possible. This is not doable with the current Monte Carlo tools. So what we did was, we imposed a PT cut on the muon pair of larger than 50 GeV. At this point, the QD showered rate is already pretty low, and the fixed order calculation is larger. And then we just took the fixed order calculation as an estimate for the mu gamma background. However, you still have to choose an IR regulator, but I'll talk a little bit more about that later on. So our assumptions here, so for a forward detector, what we assumed was that you can detect all muons which have an energy above 500 GeV, because they need to have some minimal energy to even cross to traverse the nozzle. And we assumed you can detect them with 100% efficiency.
So what if I just took that 50 GeV divided by the beam energy, what eta would that be?
The 500 GeV, or no, the 50.
So because you're doing your cut on 50, I'm just saying how many muons, I'm trying to get a sense of how many you're throwing away, right? So if you, because these less than 50 GeV PT mu pairs will also be much more forward, right?
Yeah, the translation is not completely, it's not so simple because this is the PT of the muon pair. So it's not the PT
pair.
of the, it's not the PT of the signal.
Pair.
Because in this case, it would always correspond to the PT of the missed particle that you would have here.
Did you try to estimate somehow what you're throwing away by putting on that cut?
I think it's less than what we assume for the coverage. So we assume that we cover up to an eta of 6, and I think this is roughly unaffected by that.
Okay.
Because also Higgs also has a PT that you produce, so you don't throw away that much. But this is definitely not a bottleneck as far as I know.
Could I ask
Yes.
a question? So
Yes.
the left invisible width, there was always an ISR photon to tag the events. So are you able to see this by just measuring the outgoing muons? Or do you also...
We only have the outgoing muons. We don't
ISR
use anything else.
Unnecessary.
No, not necessary. Because also it would be much smaller here because it would be a photon that you would have to make very central because the main detector has a small coverage.
Sure.
So you lose a lot of rate. Because we also thought about those things that you could do only with the central detector, and those typically have a very small rate because you have to force everything to be really central, like any kind of radiation, and then you are not really competitive to anything that you have right now. Okay. Then we took two benchmarks in terms of the energy resolution. One that is probably overly optimistic, but that's supposed to be a benchmark that tells you what the theoretically best bound would be, which is an relative energy resolution of 1%. Then a more realistic value of 10%, which is based on some preliminary simulation results that the experimentalists in the IMCC collaboration did. And they saw that 10% smearing seems to be realistic at this stage. And we assume a coverage of up to an eta of 6. And for the main detector, so the only thing that we need here is we assumed the angular coverage up to an eta of 2.5, which is the current design, and conservatively took a detection threshold of a PT of 20 GeV for any particle. So anything that's softer than 20 GeV, we assume gets lost with a background. Okay. Now, what can you do to separate the signal from background? So we found that there are essentially two main variables, kinematic variables that help you. One of them is the missing invariant mass. One of them is the minimal muon energy of the outgoing muons. Let's first look at the missing invariant mass. So in black is the signal, so the mu-h signal. And as you see, it has a tail. The tail comes from using a muon PDFs. So this is effects of initial state radiation, which smear out the peak a little bit. But it's still a pretty sharp peak. So this is a parton level, more or less, just using a muon PDF.
Sorry, what's the definition of the minimum invariant mass?
Oh, okay. So the only thing that we observe are the two muons. So we reconstruct the missing invariant mass by taking the center of mass energy, 4 vector minus the 4 vectors of the two observed muons, and then take the invariant mass of that. I'm not sure it's clear. It's just, in principle, the typical thing. You have the center of mass energy that you have, which is in the center of mass frame, and then you subtract the 4 vectors of the observed particles.
So it's the beam center of mass energy, yes, minus the measured muon invariant mass.
Not the muon invariant mass. It's it's more or less the missing 4 vector. You square the missing 4 vector.
Okay, so you look at everything that you can see, including
exactly
the muons, find its total invariant mass.
Exactly. Yeah.
That's the beam energy, beam center of mass energy minus that.
Yes.
Okay, got it.
Yes.
Sorry. Okay, thanks.
Okay, and yeah, so you really have a peak at Higgs mass. So that seems to be a very useful variable. And the other one, which was not so straightforward to us, is the minimum of the two muon energies. Because as you can see, it is very peaked at very high values, which means that the muons give very little energy to the Higgs. The Higgs is really produced on threshold, almost at rest, almost as much at rest as possible, so that the muons still have most of the energies. While the backgrounds, they fall off much quicker, and the reason for that is that we have this PT cut on the muon pair. Because having a PT cut on the muon pair, so okay, let me explain it like that. So if you sit close to here, this means that the muons gave very little energy to any particle that's produced with the muons. So any X particle has very little energy because the muons still have most of the energy left. Now if you ask this particle to have a large pt, in our case 50 GeV, and you force it to be central. And if it's central, you can veto it. This is the reason why this falls off much quicker, because even though the Higgs is still very central, you cannot veto it. So you have that in there.
This is somehow essentially the same trick, like they look for things, you know, like HBB bar, you get it by requiring the Higgs to be a bit boosted,
Yeah,
right?
yeah,
It's the same
yeah.
trick, right?
Yeah.
Yeah.
Exactly.
You lose events, but you have a lot less background.
Yeah, exactly. But here it's also helped us we peaked in this region, so this helps a lot.
Sorry, what trick are we seeing?
What?
What trick are we seeing? I don't really understand why this line goes down besides the black one goes up. It's
okay.
to have high energy muon.
Yeah, let me say again. So you have high energy muons in the final state. This means they couldn't have given much energy to anything else that's produced, right? And then we have a cut on the PT of the muon pair, which is the same as saying we have a cut on anything else that's produced, because there's nothing else, just the two muons or an X particle. And if you force its PT to be large and has little energy, then it has to be central. It cannot have much energy in the forward direction. And if it's central, then you can see it in the main detector and you can veto it. That's why it falls down. So anything that would sit here from the background, we would be able to veto in the central detector. While the Higgs is invisible, so you don't see it. So it can peak up here. Okay. All right, so then this is just, so far, this is just all very idealistic. This is at particle level. And if you then do the analysis, then you find that you can be very close to the optimal sensitivity. So I mentioned 10 to minus 4 before, and we find that here you would actually get a sensitivity of around 2 times 10 to minus 4 up if you extend the detector coverage up to an eta of 6. So this is a function of the coverage of the fault detector, and if you are at 5 or 6, then you more or less get the optimal sensitivity here. But this so far is just too optimistic, because there are some additional effects that we have not included yet. One of them, which makes the missing event mass essentially useless, is already just including a beam energy spread. So the two beams, we don't really always have collisions where both beams have exactly the same energies. Sometimes they're boosted in one direction, sometimes in the other direction, and it's not always exactly at the center of mass energy, at the nominal center of mass energy. So they say they can have a 0.1% beam energy spread, but even that smooths out the peak quite a bit. So this is still the Higgs signal and the missing bare mass distribution of the Higgs signal, and even just this tiny beam energy spread spreads out the peak quite a bit. So it gets less useful.
Because it's 0.1% of a lot, right?
Yes, essentially, yes.
It's a big energy number, so that's,
Yes.
wow.
But
I'm actually surprised, I don't know anything about that. 0.1% seems pretty good for a beam that's decaying all the time, right? I mean,
yeah.
I'm impressed.
Yeah,
That's 5 or 10 GeV.
Yeah.
Does that sound right? And,
Well, this is a 10 TeV.
Yeah, it's 10 TeV, yeah.
10
5
TeV.
GeV.
Yeah.
So it's
Yeah,
it's a factor of 1,000.
it's 1,000, so it's a 5 GeV.
5
Yeah, exactly.
Yeah.
Yeah, it's very impressive. There was also this proposal where they proposed to run a muon collider at the Higgs resonance, and they wanted to measure the Higgs, in principle the Higgs width, by just running it on the resonance. And they claimed, I think, that they could achieve a beam energy spread of 10 to the minus 5 or 10 to the minus 6.
At those lower energies.
Yeah, I don't know how realistic that is, but I know that there was this proposal.
That's crazy.
Yeah.
So the red peak gets washed out the most, I guess. Well, a bunch of them do. So
Yeah, essentially.
Gamma.
Yeah, in principle, all of them get washed out quite a bit. But the problem is, this is not the end of it, because we also assume that there is probably an energy resolution of the measured muons. So if you assume a 10% energy smearing, then it's essentially almost completely flat. Then you can't use the missing by mass, in principle, loses all of its discriminatory power. You cannot use it at all anymore. So this variable is completely gone.
Is the 10% just an incredibly conservative estimate, or has somebody tried to run some?
Yeah, somebody has tried to run a few simulations just by letting the muons propagate through the nozzles, and there they found that it was pretty close to a 10% smearing of the muon energies just by running it through the nozzles. And so this is more or less the limit. We can't do much better than that probably. If they don't come up with anything else, that's pretty smart.
You also get a lot of multiple scattering. Maybe it's all in there, but
Yeah, I think it's essentially in there. Yeah, they
It's
consider
amazing that the mu gamma goes from being completely negligible to completely dominant, right?
the mu gamma.
Right?
Oh yeah.
Right,
Oh.
and so that's somehow because the kinematics, if you're perfectly back to back, then your gamma kind of has to be pretty much perpendicular or something. There's some kinematic thing like that, right?
Okay, so here this is really at parton level,
Right.
which means that you can completely reconstruct the gamma form momentum, and gammas are massless, so they're
Yeah.
missing when mass is at 0.
Okay.
And in principle, moving a peak from 0, it always spreads out a lot. There's not much we can do, unfortunately. So the missing mass is in principle gone. The only things that are really left with is anything in the transverse direction. Also, the muon energy, the minimum muon energy that we had before is gets a little bit worse, but it's still usable. So that still helps a lot. Okay, let's go into the numbers. So we don't have to look through all of that. This is just one benchmark point for a coverage up to 6 and 10% energy smearing. The only thing that I want to mention here is that even though you have 10% energy smearing, you can still reduce the background by at least 3 orders of magnitudes. For some of them, for the photon background, even by almost 5 orders of magnitude. So you can still do a lot, even though your environment gets much more messy. And then what we find with this more realistic benchmark scenario is a invisible branching ratio, which is bound to be less than 10 to minus 3. So you use more or less 1 order of magnitude by including all of these effects. And then you can look at it as a function of the coverage of the photodetector, and also with all of these different benchmark scenarios. So the one that I just showed was this purple curve here, which assumes 10% energy smearing. And as you can see, if you have a coverage up to an eta of 5 or 6, then you're in principle at the optimal sensitivity, and you don't really need more than that. So an eta of 6 would be like perfect for principle everything. Okay, so now how does this compare to anything else? So it's even the least optimal scenario is still better than FCCE or ILC. While FCCHH, in order to get close to that, you have to make some improvements and get closer to the optimal bound. But also the analysis for FCCHH was very optimistic, so it's not completely clear if they would really get this far down. Okay, this was the invisible Higgs decays. I'm already running pretty late. Okay, then. Oh no, not completely. So we looked at the angular resolution to see if you have a finite angular resolution, if this also worsens the bounds. What we did was we just looked at one benchmark value, here eta equals 6, and just smeared the energies, the angles of the muons. What we found was that up to a resolution of 5 millirad, there's in principle no significant loss of sensitivity. So the energy resolution seems to be more important than the angular resolution here. Okay, there are a few caveats and improvements that we did in our new work, but I'll have to skip those because I'm already pretty late. Then another thing that we looked at, okay, first, are there any questions about the invisible Higgs production?
No, I'll ask at the end. It's
Okay.
unrelated.
Okay, then let me just say a few words about the inclusive Higgs production. Is this? Here. In principle, you could do exactly the same thing if you don't assume that the Higgs decays invisibly. you just assume that the Higgs can decay into anything, then you can do exactly the same analysis and just try to measure the inclusive Higgs production in ZZ fusion. The only difference is that now you can of course veto nothing in the central detector. The only thing that you can work with now are the two muons in the forward direction that you observe. And in that case, you can still work with the minimal muon energy, slightly less effective because of the effect that I mentioned earlier on, that if you can veto anything in a central detector, then you move the drop-off of the backgrounds to the left and you have a clean separation. Now it's not as clean anymore, but you can still use it, and you still gain by using it. And the only other thing that you can use is the PT of the muons. And so this is showing the minimum of the two PTs of the final muons. And as you can see, the Higgs signal, which is again in black, it drops quicker than all of the backgrounds. So having an uppercut on the PT still helps a little bit. And then what we did was simply a simple cut and count analysis here, that we go for 1 and 10% energy smearing. We impose some cuts on the minimal muon energy and the PT. And for 1%, you can also use the corresponding quantity to the missing event mass, which is here the reconstructed Higgs mass. There it's still a little bit useful, while for 10%, again, loses all of its sensitivity. And what you find in the end is that you can measure the inclusive Higgs cross-section, so the relative measurement with respect to the standard model, of the order of 0.5%, so half a percent, which is pretty impressive for, in principle, almost not vetoing anything, just letting it run, which is in principle just because the numbers of Higgs are so huge. So even before any cuts, it's already comparable to most of the backgrounds. And once you do a few cuts, you can make them comparable, and then just get a signal background of like 10% more or less. But just because you have so many Higgses, you can do this measurement, otherwise you couldn't do it.
So when you're talking about exclusive, in practice, you're talking about the sum of those particular modes? Is it really insensitive to the, I mean, here you're imagining that, I don't know, there could be something like some big cross-section for H goes to jets, which you couldn't measure in an exclusive way very easily or something, right? Mm-hmm. And so, but this number is really insensitive to what is it that the Higgs is decaying into? It's really insensitive to that?
So,
because I would have thought you'd have different efficiencies for all these different final states and things like that.
well, we don't look for an explicit final state. We allow everything. And also in our simulation, we just produce an orbital Higgs and let Pythia shower it. So everything is included.
But I'm just saying that
so we don't
the
look at
different
the
final
picture.
states for the Higgs, you'll have different efficiencies for them. I mean, an extreme example is the invisible Higgs,
Yeah.
where you'd have no efficiency at all to see what it is, right? Now you're assuming, on the contrary, it's going to standard model particles. But
We don't assume anything. So this can be anything. We don't look at any of the central objects. We only work with the forward muons.
But you're reconstructing, I mean, you're measuring a PT based, okay, maybe I'm not understanding, but I mean, basically I thought you were inferring the PT by measuring all the stuff, all the standard model stuff you see, right? And in this scenario, some of that's coming from the Higgs decay. No?
So this is like the diffractive physics that Mike Albro always wants us to do, where you don't look at anything in the central detector, I think.
Yeah.
And
Oh, you're not,
only-
I'm sorry, this is
only
using
looking-
nothing from the central
Yeah,
detector.
That's
nothing.
That's what I didn't, okay, sorry, I guess I'm sorry, that's a
That
very
was good to clarify.
basic point.
Yeah, I
didn't
should have put that on the
miss
slides. Yeah, I just
No, I'm
nothing.
sure you said it,
Yeah,
right.
nothing is detected.
And so then I'm sorry to be slow, so then if you're only using stuff from the central detectors, or nothing from the central detectors,
Yeah.
what's the difference then between this and the invisible decay?
In the invisible decay, you use stuff from central detector because you use it to veto backgrounds which are not invisible.
I got it.
You're more or less
It's the other
just
way
selecting
around,
everything.
right, it's in that
It's
case.
more restrictive, more or
It's
less.
in that
yeah.
case, right, and then
Yeah.
you know, of course, how much stuff you have, and got it.
Yeah.
Okay,
yeah.
thank you.
Invisible is just more restrictive. So this is like doing like almost the dumbest thing. You just turn it on and see what you see, and do a few little cuts.
Okay, thanks.
Okay, just as a comparison, this has also been done by a different group, and they find a little bit worse bound, but we found that this is due to less optimal cuts that they use, and they have a different modeling of the mu gamma background, which I think is not completely correct, but don't have time to comment on this anymore. And then you can also interpret this as a measurement of the HZZ coupling, and provide it that way, then this would correspond to a determination of a relative accuracy of 2.5 times 10 to the minus 3. And that you can compare to FCCE, where they expect to be able to constrain it to 1.7 times 10 to minus 3. So even just this inclusive measurement without doing anything fancy is very close to FCCE.
So in the standard sort of kappa numbers that you see, are they also make the same assumption that any invisible change to the invisible width is due to HZZ? That's the essential assumption here, right? Or
Yes, yeah.
and that is the standard assumption that people make when they quote the kappa for HZZ, right? I think.
As far as I know, yes.
Yeah. Okay.
Okay. I'm running really late, so you can choose. Do you want to see Higgs portal models or the angles, the interference resurrection? Any?
I would vote for the angles, but
Okay.
Marcus speaks for everyone.
Okay, good.
I mean that's just me.
Then let's do the angles. That's something different, so it's nice. Okay, then let me just show the results of the Higgs portals. So, okay, let me just say one word. So we looked at two different Higgs portals, both scalars. One was the renormalizable Higgs portal, so the one that you typically see, and the other one is a derivative Higgs portal, which is inspired by PNGV dark matter models. And in both cases, we assumed the nightmare scenario, as it's called, where there's a C2 symmetry and the scalar is stable. So it's like missing energy in the detector. And what we find is, okay, it's a very busy plot. This is just a comparison to our results to anything that we found in literature. And the important lines here are the blue and yellow lines, which are our results. So this constrains the portal coupling with respect to the mass of the scalar. And for the blue line assumes energy resolution of 10%, and the dashed line assumes something for the central detector. But let's just focus on this blue line here, which is like the least optimal case that we would have, and even that is more sensitive than FCCHH.
So what are the dashed lines that look like they are more sensitive? The FCCHH glue to 4L?
Oh, that here? Yeah, that's an indirect probe. So this model there, you compute the loop contribution of the Higgs portal scalar to this process here, so glue to 4 leptons.
Got it.
But in terms of direct bounds, this is what we have is the strongest. Anything that's dashed in the other colors is indirect.
Okay, thanks.
Okay, for the derivative portal, it's pretty similar. So again, so this is constrains the coupling. This is a dimension 5 coupling. So you have dimension 6 coupling. So you have a suppression scale, and we can constrain a suppression scale here up to about 1 TeV for a large range of masses. And if it's really dark matter, then you would be sitting somewhere along this thermal abundance. Unfortunately, this thermal abundance goes up pretty quickly, so you would not be able to constrain much of it being dark matter, but it's still the best bound that you could get. So like the least optimal scenario is comparable to FCCHH. Alright.
Do you just use the Higgs strictly invisible width to do the analysis, or do you do something more?
You mean the analysis here?
For this
No, we don't use the invisible width here, because here we are talking about offshore Higgs. This is yeah, this is masses above half the Higgs mass. So it's a dedicated analysis. So the kinematics is slightly different, and but the idea of the analysis is still pretty similar to the invisible Higgs width, but the kinematics are slightly different, so you have to work a little bit harder to extract it. All right, the angles. Okay, so this is a completely different direction now. So as I mentioned earlier on, even if you just have angles of the four muons, you can already do a lot of physics with that. And the reason for that is that, well, if you measure total cross sections, for example, then you're looking at an integrated observable, which means that often, if you look at integrated observables, then you don't have interference of, for example, standard model and DSM contributions of the amplitude. You often integrate that out because often it depends on angular information, and if you integrate over angles, then they drop out. We will see that in a second here. But if you keep angular information and have, especially in this case, have the angular information about the muons in final state, then you can resurrect, or you're sensitive to these interference terms. In order to see that, let us just look at, again, just a muon collision, two muons and the muons plus some x, and let's look at it in the effective vector boson approximation. So in that case, you can describe it in terms of a factorized process. So we first have the splitting of Z bosons, in this case, for example, from the mu plus and the mu minus, and then these two Z bosons take part into in the hard collision process that produce some final state X. And this is typically only valid for an invariant mass of the X final state that's much larger than the vector boson mass and the PT of the muons. But even if you're not in this validity, you can still get some qualitative information. And it is actually most useful to describe this in terms of density matrices. So in this case, I know it looks a bit intimidating, but it's actually pretty simple. So you just factorize the cross-section here in terms of two density matrices, which are responsible for the emission of the Z bosons, and then one for the hard process. And when you write them out, then they get pretty simple. So in terms of the hard process, this is just the scattering of two Z's into an X final state. But as you can see, there are a couple of helicity labels here, in principle more than you think would be there. So there's, because here the original amplitude and the complex constant amplitude have different helicity states. You can think about this like when you have an amplitude and compute the amplitude spared, then you have cross terms, and each of them comes with their own helicity sum. This is why you have different helicities for these in the amplitude and its complex conjugate. And then of course you have to sum over all of them to get the cross-section. And the same is true for the splitting amplitudes here, where you also have different helicities and have to sum over them in the end. Now in the following, I'll just focus on the azimuthal angle phi dependence, where phi here will be phi of the mu plus or of the mu minus in the final state.
So sorry, can I think of this sort of physically? I mean, the initial muons are not polarized, but are these Z's polarized or somewhat polarized? Is that a way to think about this? Because it seems like if the Z's were not polarized, then if they were perfectly unpolarized, you would just be averaging over the initial Z polarizations. Isn't that right? So is it somehow the fact that this works is related to the fact that these Z's are somewhat polarized, even if the muons are not? Is that correct at all? Or?
They're in principle not polarized. You just have you have them in different chirality eigenstates. So we have plus, minus, and longitudinal.
Yeah.
And then when you write down the sub-amplitudes for these helicity, well, if you take a master for these helicity eigenstates, then different operators or different interactions only contribute to some sub-amplitudes. And then typically, what you typically have is that when you compute a full cross-section, and different helicity amplitudes don't mix. You always have the amplitude spared of each helicity amplitude, but if you keep the angular information, then you can get cross terms of those that stay. It's in principle cross terms of different helicity amplitudes, or interference of different helicity amplitudes.
But that can happen even if, let's suppose I just had Z-beams here, and the Z-beams were perfectly unpolarized. I would still have this effect?
No, there'd be no interference then, because you'd only have one helicity state.
Yeah.
Yeah.
Well, no. Unpolarized means I'm averaging over all polarizations, not
You just
that I
said
have one
Z is
polarization.
polarized. No?
What do you mean the Z is polarized? There's three helicity states.
But I
and
assume they want
If
to
I
see the
average
muon.
over all three helicities,
Yeah.
if I say I have
Yeah.
a perfect,
If you only have Z, you don't see the muon, right?
Yeah.
that's true too. But I'm just asking if I'm understanding the basic physics of this correct, is that the fact that there's the interference resurrection is that the fact that if you don't sum over all the angles of the x's, then you can get some interference, right? Which gets washed out if you do
Yeah.
average over the angles of the x's. And I'm asking whether that still happens if you don't if you have perfectly unpolarized z's. I know that that's you have to see the muons to do this, but I mean,
In principle, they are unpolarized here. You sum over all of the helicities of the intermediate z's.
right.
In principle, is, I would say
Sure,
it's the
but
same
they're
story.
weighted by the production, right? So I'm asking if the, it's okay. Why don't you go on, because you're running out of time and
Yeah.
we're stopping you a lot.
Okay,
Sorry.
okay. Okay, so I'll just focus on the azimuthal angle of the muons in our case, so the mu plus and the mu minus. And in that case, if you just look at the splitting amplitudes of some A to B and C states, then just from rotation symmetry, the dependence on phi has to be of this form. It's an exponential of minus I, and the sum of the final state helicities minus the initial state helicity.
Right.
Then you have a simplification in our case where A and B are muons, because the standard model interaction is chirality preserving, so the helicities or chiralities of the muons don't change. So HA is HB, which means that our splitting density matrices are just proportional to e to the minus I, H1 minus H1 prime, times phi plus, and the same for the mu minus. And those are just the azimuthal angles of the two muons. Now when you go back, so you have to sum over all of these helicities, which means that each term has really a characteristic dependent on a pretty big simplification here. You have the hard scattering here, and you have two terms which depend on phi plus and minus. Oh yeah, here it is, phi plus, phi minus, which is multiplied by the delta of within this amplitude, so the delta of the z and z in the amplitude and the z in the Hermitian conjugate amplitude.
So so delta H1 is the difference of which helicities? I'm sorry.
So it's always 1 and 1 prime are within the same splitting. So it's always one is the helicity of the amplitude in the amplitude, and one is the helicity in the Hermitian conjugate amplitude that they
Oh,
multiply.
right. Okay, I got it. Right.
And here you can see that this would actually vanish when you integrate over phi plus or phi minus. Because this would just be like a cosines and sines, and you integrate over a full period, so this would always vanish. You would always only keep the term where the delta H is 0. So what you would naively expect, like the diagonal piece, where the initial, where when in phi in A and A star, you have the same helicities. So, and since the phi plus and phi minus are the angles of the forward muons, if we don't absorb these forward muons, and all observables that we could ever measure are just inclusive observables, which are integrated over these phi's, so we can never observe these interference effects. Let me give you an example, and then it will get much clearer. So we look at CP violating HCZ couplings. So we have the standard model Higgs Z coupling here, with a coupling modifier ZZ, and a CP violating coupling Z tilde. And now, okay, first as a baseline, so the current bound from the LHC bounds this CP violating coupling to be order 1 essentially. Now it turns out that a sensitive probe of this is delta phi, which is the difference of the mu plus and mu minus phi's. And we look at it again in VBF Higgs production. And that this delta phi is a very sensitive observer to this z tilde, can be very easily seen, qualitatively at least, in this in the formalism that I just introduced. Because here you have the different helicities for helicity amplitudes for the hard process, so Z1, Z2 to Higgs. And as you can see for the plus minus configurations, this is clearly helicity violating because the Z tilde contributes different signs to different helicities. And then you also have the longitudinal contribution, which will not be very important right now. Now, as we see here, the only possible contribution is when both Z's have the same, the helicities have the same sign. Only then you get a contribution to the helicity amplitudes, which means that in this term here, so the delta, so the H1 and H2 is the same, and the H1 prime and H2 prime is the H1 prime and H2 prime is the same. So our differential cross section simplifies to this term here. So you have an e to the minus I delta H times delta phi times the hard the hard process density matrix. And the only delta H's that are possible here are 0, plus minus 1, and plus minus 2. Because you can either have a plus and a minus helicity configuration, or 0 and 0, and 0 and 1, of course. What this means that when you write it out, because you sum over all of these helicities, the function form has to be a constant, a function of delta phi, and a function of 2 delta phi. And these are always trigonometric functions. And since these are trigonometric functions of delta phi and 2 delta phi, when you integrate over phi over the full period, those would always vanish, which means that the constant term is proportional to the total cross-section. Now, we can just do some simple analysis. Delta phi is a CP odd variable, and C tilde ZZ is the only CP odd spurion that we have in our theory. So we can directly write down like the full dependence of the differential cross-section on delta phi. You always have one, so the Z squared, the standard model contribution, and the Z tilde squared above CP even. So they can only have functions, have cosines of delta phi and 2 delta phi, while the CP odd term here, which is an interference contribution of standard model with BSM, depends on sines of delta phi. And we checked it through simulations, and you find a really good agreement. So in blue, red, and green, you see the different functional contributions in here. So you see that red and blue are the two CP even contributions, and these are symmetric around 0, so the blue is symmetric around 0, and also the red, while the green, which is this contribution here, is CP odd, so you have an antisymmetric function around 0 of delta phi. And when you add it up, so this was for a Z tilde of plus 0.2, and you get this black curve here, which you also see it in gray, which is the Monte Carlo simulation. It agrees excellently. So what it can do now is construct a variable that's only sensitive to this interference contribution, and that is, so the simplest that you can find, is just a forward-backward asymmetry. So we define the asymmetry as being the events which have a delta phi between 0 and pi, minus the events between minus pi and 0. And this exactly picks out this contribution here, because this and this, they integrate to 0 if you take the asymmetry. And then you have something proportional to Z tilde, and the standard model coupling Z. And then to break the degeneracy means you need an additional measurement, which could be, for example, the cross section in whichever channel you're looking at right here. And what we looked at was the BB bar decay channel of the Higgs. Okay, then there are two steps. First, you extract the Higgs signal, which in our case is in the BB bar decay channel, from the background, and for that we just did very simple things. We just asked for 2 V-jets with PT of larger than 30 GeV, and you can also cut out the BV bar invariant mass around the Higgs peak. Just note, in this case, you measure the B's in the central detector, so here you don't have the problem of this large energy resolution that makes the invariant mass uses in previous studies almost impossible. If you do that, then you find that that you have pretty good accuracy on the cross-section measurement. So we curiously found that if you don't include a cut on MBB, then it's actually better, but you get a smaller signal over background. And this measurement or this estimate is also in agreement with an earlier study by Patrick Reed and company. Now the interesting thing is when you use that now to construct the asymmetry, and we did that, and we found that you can set bounds on this combination of coefficients, which are of the order of 10 to the minus 2. And if you think back to the LHC, there it was around 10 to the minus 1, like 5 or 6 times 10 to the minus 1. So you get more order of magnitude improvement compared to high Lumi LHC. And then you can do a combiner analysis and disentangle the standard model coupling modifier and the CP variation coupling, and just get a combined bound over time. So I'll just mention very, very briefly how this compares to other future colliders. In order to do so, you unfortunately have to introduce this very unfortunate variable, which we don't really know why people use it. And we find for this variable, for which you have to assume that the Z coupling is standard model-like, we find a bound of the order of 10 to the minus 6. And so compared to high Lumi LHC, it's better by 1 order of magnitude, while for future A plus and E minus colliders, it's better by at least 1 order of magnitude. So it seems like the Muon collider is also outperforming our colliders here. Okay, this is my conclusion slide. I just want to flash again all of the different things that you can do with forward muons, and I hope I've convinced you that a forward muon detector would allow for great physics at a Muon collider, and that it definitely deserves some consideration by experimentalists and some dedicated study. All right, thanks.
Questions?
I think.
So for a HBV CP paradigm coupling, is that within standard model or is motivated by some theory that people always do?
It's not within the standard model, so this would
It's
mean...
mostly motivated by what type of theory?
Well, you can construct many things. So typically the values that we can constrain here, it's hard to find sensible UV completions for that because the values are so low. One thing that would produce something like that, you can, for example, just add 2 vector like Lepton multiplets with these quantum numbers under SU2 and U1, and when you integrate them out, then you, among others, generate this Z-Tilly coupling that we constrained. And within this model, with our most optimistic bounds, you could constrain the mass or the suppression scale of these operators to be larger than 340 GeV. So that's one way to generate it.
I mean, people tell me supersymmetry or axion or something. So, like, what type of? Is this a dark matter candidate or why these two?
This is not really a dark matter candidate. This is a model which can give you CP variant couplings to vectors, which is actually not that easy to generate.
Okay.
So
if we find some CP variety in that parameter, then it's definitely new physics.
this would absolutely be a sign of new physics. Yes. It's something that you should check. People do check, and some take it very seriously. But to do it from the top-down way, it's actually much harder.
Okay.
Yeah, I guess I didn't completely understand the forward backwards. What's
Okay.
forward and then backward? You
Okay.
observe BB band and you have some nuance and what exactly forward? What do you call forward? What do you
Okay.
call backward?
Yeah, it's maybe a little bit of a misnomer. So the forward is more or less just defining. So we in principle have, where is it? In principle, you might make a cut here, and everything that has positive delta phi values you call forward.
Delta phi. What experimentally what is exactly the measure for delta phi?
Well, for delta phi, you measure the phi of the mu plus and the mu minus, and just take the difference. It's just the difference of the two lengths.
So you'll be able to tell a mu plus from a mu minus in the forward region?
Right. Yeah.
You're assuming that, yes?
Well, yes, we're assuming that, but even if you cannot measure charges, you know that from which direction the mu plus and from which the mu minus is coming, typically
right.
they go straight. So
Oh, of course.
even if you can measure charges, this would
Yeah.
be almost
When they are back to back, you call it zero.
What-
Exactly back to back.
This is
The
azimuthal,
mu plus
This
and
is,
right?
this is an azimuthal direction.
Yes.
So it's
Then you call it zero. Is that
yes.
delta H would be zero if they are exactly back to back?
Yeah, delta phi. Yes, when they are back to back in the azimuthal direction. Yes. Then that would be delta phi equals. Oh wait, delta phi equals. No, notice delta phi equals 0 would mean that they
Or
are.
in the stem?
Yeah, that they're the same phis.
So pi.
Yeah.
It's this way you call it zero, or this way you call it zero.
0 is if they really have exactly the same phi.
But
So
he's
this
saying,
way.
are you asking that theta equals 0? Then it's just undefined, right?
No, I'm asking phi.
Phi equals
Phi,
0.
the
Yeah.
phi is that means
Yeah,
like
yeah,
Yeah,
right?
they're the same
So-
phi. If they're in the same plane, more or
So
less. If they're in the same plane, then you have delta phi
if
equals.
this is zero,
Yeah, if they're in the same plane.
if they are back to back, you call it pi.
Yeah, I think that's right.
Yes.
Back to
yes,
back
yes.
is pi.
Oh.
Okay.
Yeah, well, invincible is just a definition.
No, just
Yeah. But yeah, it's a good question. It's always, these angles are always hard to figure out. But in principle, forward and backward, maybe you shouldn't call it forward and backward. It's just, you divide it into two bins, like more or less this. The forward
Actually,
bin
you
is the
can-
one between
You can
delta
tell
phi.
that because he has the opposite sign, right? They come in with
Yeah.
the opposite sign. You see what I mean? So one of them is they would come in the same sign if they were rotated relative to the momentum. They're coming in with the opposite sign, so they're, right?
yeah. What would you call it forward backward? That's different from my notion of forward backward.
Yeah, that's right.
It's,
Yeah, it's true. The name is maybe not the best. Yeah, in principle, it's really just two bins. We call this forward, this backward, and we just subtract the number of events in those two. Yeah.
It's more like a, I don't know, left-right thing, of course. But
It's a cosamuthal and anti-cosamuthal.
Yeah. Essentially.
clockwise or anti-clockwise something.
Yeah, yeah. Yeah, forward backward is definitely maybe a little bit confusing. Yeah, I agree.
Any other questions? You're allowed one more.
So when you're looking at forward, backward, give you better precision on kappa? Are you just using the data in the forward, backward detector, or you're also using the center bar? Like,
Do you mean for our analysis?
there's a
or-
slide that if you add this detection of the forward, backward region, you have a better percentage on measuring kappa, all the kappas, kappa, backward, kappas in.
But more information always gives you better sensitivity.
So it's just it's not like when you're using the forward backward, you just don't care about the center. You do have to also include the center part to have a better resolution.
Well, if you want to do, in principle, if you want the best that you can do, you include all the information you have and use fully differential distributions. Then you would get the maximum information you could get. But nobody has done that yet, at least not from Muon Collider. But for the p violation, it's enough to have the angles. okay, not completely enough because you also have to extract the Higgs signal first.
And that is from the central region.
Yeah, you reconstruct in our case the BB bar, so the two beachheads in the central detector.
Okay, let's thank Max again.